When you look at a solar panel, it might seem like a miracle that these flat slabs of glass can capture energy from the sun and transform it into the electricity that powers our homes and businesses. But the truth is, this transformation is nothing short of brilliant scientific design. Today, we'll break down how solar panels really work, taking you from the sun's rays to the wall socket and explaining the science behind this incredible technology. We'll start by talking about where solar energy comes from. And if you've been here before, you already know that it comes from the good old giant ball of burning gas that gives us light and warmth. But it doesn't stop there. The sun emits energy in the form of electromagnetic radiation, including visible light, ultraviolet light, and infrared radiation. Visible light is what we see, and infrared radiation is what we feel as heat. But the really important part for solar panels is the infrared radiation, specifically photons with energy levels ranging from 1 to 3 electron volts. Photons are like little packets of energy, and they carry the sun's energy to Earth. That energy travels 93 million miles in about 8 minutes, and when it hits a solar panel, the real magic begins. But before we get to that, let's talk about how light interacts with materials. When a photon hits a material, it can be absorbed, transmitted, or reflected. In the case of solar panels, we want as many photons as possible to be absorbed, so that the maximum amount of energy can be harnessed. This is where the first critical component of a solar panel comes in, the semiconductor. Most solar panels use silicon, a semiconducting material that absorbs photons in the infrared spectrum and releases electrons, which are negatively charged particles that make up electric current. This process is known as the photovoltaic effect. Here's how it works. When a photon strikes the semiconductor, it can dislodge an electron from its atom. The electron is then free to roam around the material and generate electricity. But this roaming electron doesn't just happen randomly. It's carefully guided by another key component of the solar panel, the electric field. The electric field is created by connecting a positive and negative terminal to opposite sides of the semiconductor, creating a potential difference or voltage across the material. This voltage attracts the negatively charged electrons to one side of the material and positively charged holes to the other side. Holes are missing electrons and act as if they have a positive charge. When the electrons and holes recombine, they release their energy as electricity. The beauty of this setup is that it harnesses the natural tendency of electrons and holes to move towards opposite charges. By controlling the movement of these particles, solar panels can efficiently convert sunlight into electricity, but there's a lot more going on under the hood. For instance, there are 2 types of semiconductors used in solar panels: N-type and P-type. N-type material has extra electrons, while P-type material has extra holes. When they meet, an area called the depletion region is created where electrons and holes can't move freely. This region acts as a barrier, preventing the electrons and holes from recombining and releasing their energy as heat. Instead, the electrons build up on the N side, creating a negative charge, and the holes accumulate on the P side, creating a positive charge. This separation of charges forms the electric field that drives the photovoltaic effect. This separation of charges doesn't last forever, though. Eventually, the electrons and holes will recombine, releasing their energy. But solar panels are designed to collect the electricity before this happens, creating a closed-loop circuit that drives electric current. But before we get to that, let's talk about the materials used in solar panels. The most common material is silicon, a relatively inexpensive and abundant element. However, pure silicon doesn't conduct electricity very well. So impurities or dopants are added to create N-type and P-type semiconductors. Doping is a process of introducing impurities into a pure material to change its properties. In the case of silicon, small amounts of arsenic or phosphorus are added to create N-type silicon, and small amounts of boron are added to create P-type silicon. The doping process changes the way that silicon atoms bond with each other, creating areas where electrons can move around more easily, making them ideal for conducting electricity. Now let's go back to our discussion of electricity. As the electrons and holes migrate to their respective sides of the solar panel, they create a current. To collect this current, metal contacts are attached to the top and bottom of the solar cell. These contacts form an electrical circuit that allows the electrons to flow from the negative terminal to the positive terminal. This flow of electrons is what we call electric current. A single solar cell can produce only a small amount of electricity. So to meet our energy needs, many solar cells are connected together to form a solar array. Solar arrays consist of multiple cells connected in series and in parallel to increase the voltage and current output. The beauty of this design is that it harnesses the natural tendency of electrons and holes to move towards opposite charges. By controlling the movement of these particles, solar panels can efficiently convert sunlight into electricity. Of course, that's just a simplified version of what goes on inside a solar panel, but it should give you a sense of the brilliance of the design and the science that makes it all work. Now let's take a look at some real-world examples. Solar panels come in a variety of shapes, sizes, and efficiencies. Some are designed to be mounted on roofs, while others are designed for ground installations. The choice depends on factors such as the available space, local building codes, and environmental conditions. For residential use, solar panels typically have a capacity of 250 to 400 watts. Commercial and industrial solar installations can range from a few kilowatts to several hundred megawatts. But what happens after solar panels generate electricity? The answer depends on whether you're talking about off-grid or on-grid solar. Off-grid solar systems are typically used in remote locations where grid electricity is not available. These systems usually include solar panels, batteries, and a charge controller. The charge controller regulates the flow of electricity from the solar panels to the batteries, ensuring that they are charged properly. On-grid solar systems, on the other hand, are connected to the local grid. These systems may or may not include batteries, and they rely on the grid to distribute electricity. On-grid systems can also benefit from net metering, which allows customers to sell excess electricity back to the grid. The future of solar power looks bright. Advancements in technology are leading to more efficient and cost-effective solar panels. Perovskite solar cells, for example, have shown efficiencies of up to 25% in lab settings, and thin-film solar cells are becoming more popular for their flexibility and lightweight design. Solar power is also becoming more integrated into smart grids, allowing for better management and distribution of electricity. So the next time you see a solar panel, take a moment to appreciate the brilliance of the design and the science that makes it all work. From the photovoltaic effect to the delicate balance of electrons and holes, every step in the process is a testament to human ingenuity and the power of science. And as technology continues to advance, who knows what new innovations we'll see in the world of solar power. Thank you for tuning in, and stay tuned for more updates.